Today we'll be doing the bean lab, in which we're going to try to model isotopes as well as determine the average atomic weight. We'll have three different kinds of beans in our bean bag. One bean will be the large limas. The smaller ones will be the kidneys, and the tiny itsy bitsy ones, those are the navies. The bean bag itself represents a sample of atoms, for which in this sample there are different kinds of atoms of the same element. This is similar to how isotopes exist for a certain substance. So our goal today is to try to figure out what is the average atomic mass of bean in a bean bag. The first thing we'll do is we're going to mass each bean. So we'll get a large one and a small one and a tiny one and mass them using our balance. Now what you can do is you can get maybe 5 or 6 of these and average them. You can get about 5 or 6 of the kidneys, average them, and 5 or 6 of the small navies and average those masses to get the average mass of one bean. These masses might come out to be 1.0 grams, kidneys might be 0.55 grams, and the small navies might be 0.11 grams. The second thing we'll have to do is determine the number of each bean. So if you have a bean bag, you're going to have to go ahead and separate all of the different kinds of beans. Let's assume I did that very quickly. Here's a sample of large limas, and here's my small kidneys, and here are the small navies. Now rather than counting each bean, think about a way I can go ahead and count without counting. Excuse me. So we're going to count how many beans we have, and maybe we might have 427 limas and 311 kidneys, and it might be 812 of the small navies. From there, we'll have to figure out the percent abundance, okay, which would be 427 over the total number of beans. Likewise, 311 over the total number of beans, and 812 over the total number of beans. Relative weight, this is the one that people have the hardest time with. Take your percent abundance and multiply it by the mass of the bean. Take the percent abundance and multiply it by the mass of the bean, percent abundance, multiply it by the mass of the bean, and then the last step is add up all those relative weights. So beans, these might be the lightweight isotopes of an element, another isotope of an element, and the last isotope of an element. So starting with this, we'll end like this, and we'll end up with an average atomic weight of benium.